when we are considering closed enclosure, let's say we have got a box where we have got a number of gas molecules, okay, and if we actually want to have an idea of how are these gas molecules distributed, we use something which we call as the Maxwell Boltzmann distribution. Okay, so this is something which we are going to see now, and I hope all of you have joined in. Okay, I'm just starting off looking at the people there. Okay, so we got two boxes here. Okay, let me just give you a very brief idea. Okay, so just listen to this like a story. Okay, you have a box, box one. You have got one more box, box two, and there are gas molecules within this box. Okay, and you can't really predict the direction along which they will move. Okay, so they are moving randomly in different directions. Okay, they are colliding. If you consider a real system, they will obviously keep on colliding, have an impact because of the restrictions that they have, that will also have an impact, and so on. But what is the basic idea? The basic idea is that if you have temperature, let's say T1, and we have got temperature T2, if this temperature is greater, okay, if the temperature, let's say in box 2 is more than box 1, the gas molecules which are present in box 2 will actually move around more vigorously. Okay, more vigorously, the chances are there. Okay, and that means their energy will more or less be more. Okay, but on the other hand, if the temperature is less, the chances are that their energy will be less. Okay, so this temperature which is there for the box will actually govern the average kinetic energy. The question is, why the term average kinetic energy? So when we actually want to analyze a box which is filled with gas, we don't consider a single particle and try to analyze it. That is not possible, not feasible, doesn't sound practical. So what we do is we consider a number of gas molecules, okay, and study their average kinetic energy. Okay, so that's why average kinetic energy is an important concept. Okay, so this is what we do in Maxwell Boltzmann distribution. Okay, but as I told you that if I have a box where the temperature is more, definitely the speed is going to be more. Okay, so what I said here is that T2 is greater than T1. Okay, so let's do a distribution here, number of molecules. Okay, so I've written here number of molecules. You can write it as number of particles. Okay, anything, number of particles, number of molecules means the same right now. And then along the x-axis we have got the speed. Okay, along the x-axis we have got the speed, and this is the number of molecules. So if we are considering, let's say, the speed, okay, so if the temperature is not very high, the speed is not, the maximum speed that we'll be having will be, let's say, somewhere here. Okay, assume it somewhere to be here. Okay, and then this is the distribution of the speed, because you see all the molecules cannot have the same speed. Okay, some of them particle will have maximum speed. So what happens is, if we look into the temperature T1, and if you look into this particular point, let's say this is your speed V1, the maximum number of molecules will have this speed. But then there will be some molecules which will also be having a speed lesser than this. Okay, because that is a practical idea. Okay, it will have a lesser speed than this. And then some of the particle might have slightly more speed than this also. Okay, and in this way we can actually have this distribution graph. So this is how it is distributed. So it looks like a bell-shaped curve. Okay, and if you remember your statistics, this is looks like a more of a normal probabilistic distribution. Okay, so this is a distribution, no doubt. But then if I increase the temperature to T2, the chances are that the maximum number of molecule will have a speed V2, which is of course greater than V1. Very logical. But then again, there will be some which will be less, some will be which will be more. Okay, so in this particular point means the speed would be very less. That means it will almost be zero. But the chances of speed being almost zero when you are actually having a temperature T is minimum. That's why here the number of particles are minimum. Very less number of particles are there. Okay, the probability is very less. So this is how the probability distribution curve for Maxwell-Boltzmann distribution is. Okay. So can we just read a statement? I think I've kept this enough time on the screen, so you can just read it through. Okay, the statement says that the Maxwell-Boltzmann. Okay, so gives the total energy of a system. So you see, speed, that means potential. Speed, that means we're talking about velocity. That means we can comment on the kinetic. If you know the velocity, we can comment on the kinetic energy. So gives how the total energy of the system is distributed among various member of an assembly. You basically have a closed and how is the energy distributed among them, okay? Having identical but distinguishable particle. As we proceed towards this statistical mechanics course, you will see that this word distinguishable, indistinguishable plays a very, very important role. In the third unit, you are going to talk about ensemble, okay? There are ensemble, grand canonical ensemble, micro canonical ensemble. Okay, those ensembles have a very important part in statistical mechanics, and they are based on this idea of distinguishable and indistinguishable particle. So what do we mean by distinguishable particle? That means that if you actually have a box, okay, if you have a box and if you have a particle, let's say A here, B here, C here, these are all different molecules, okay? They might be identical, so they will be the same, okay? They will be the same. So they will be the same, let's say you have got 3 molecules. All these 3, let's say oxygen molecules, will be those 3 oxygen molecules, but you can identify them at any instant of time. So even if you apply some temperature, okay, somehow you have marked them, okay? This is an assumption. Somehow you have marked them so that you can say that even if the temperature is high and the molecules are moving here and there, after a time t, even if A comes here, I can identify it and I can say that yes, this is A, this is B, this is C. So this is distinguishable. They are identical, but they are distinguishable. Okay, so please try to understand the importance. Okay, so that's why I've just emphasized on this writing part: identical but distinguishable. And of course, we don't have any restriction on the number of particles or state. This removal of restriction actually gives us better result, because you see, if you are going to find out an average, if you are having a large number of observation and then you find the average, you are actually closer to a more realistic value. If you're taking 3 or 4 observations, you're finding out an average of that, you might find that it is not very close to a realistic value. Okay, so if there are 10 students in a class and then you are taking an average mark, the average mark that comes will be very far from a student who did not score well or a student who scored very well. Okay, but if you take a class of, let's say, 100 students, okay, and assuming that all of them are okay students, okay, and then you take an average, you will see that the average mark will be not very far from the maximum mark or the minimum mark. Okay, so that's why if you consider a probabilistic distribution, the larger the number of particles, more closer you would be to the reality. So that's very important in probabilistic idea, okay, or probabilistic study. So what I will do is, for Maxwell Boltzmann distribution, we are going to consider a situation here. We are going to consider a scenario. Okay, so let's just read this scenario once. Okay, so I think I have already said this, but let's just repeat this. So what we do is we will consider an assembly of gas. Okay, containing total number of molecules n. So you have got an assembly of gas n, n1, n2, n3 up to nk, okay? And the total molecule is nothing but n. In phase space. So that means, if you remember from classical mechanics, configuration space, phase space. So phase space means the path of the gas molecule can also be defined well, okay? So you do have an n-dimensional space, okay? And let's divide this phase space. If you look into the diagram, you can easily remember it for exams also. You can divide the phase space into the number of cells, 1, 2, 3, up to k. So in simple words, when you write down for your exam, it's not that you have to copy these exact sentences, not needed, right? If you just simply remember this diagram and remember whatever I'm explaining right now, you can just make your sentences and that's all. You don't need to worry about memorizing anything, right? And anyway, physics is not about memorizing, it's about understanding. I hope you understand that by now. So we have into a number of cells, we do have it 1, 2, up to k. This will basically contain the number of particles n1, n2, n3, n4 up to nk. So if this is cell 1, this is cell 2, this is cell 3, and we keep on going, and this would be cell k. And cell 1 has got n1 particle, cell 2 has got n2 particle, and cell k has got nk particle. Okay, that is what is said here. That's very simple. And it's in equilibrium state. Remember those three laws that I said on equilibrium state? We are basically going to use it. Okay. And now, when I'm asking you in exam, derive a relation for Maxwell Boltzmann distribution, you don't really need to derive this probability. But this probability is something which I have done in the first part of the class. Okay, so this is already done. You have to refer to that. That why do I get this? Okay, so see, this is basically a summation. Huh? Don't get confused here. Okay, it is also a notation for summation. You use this. So the probability is given by this. So this is something which I already do. Okay, subcontainer. Okay, and then this is the number of particles. Okay, and so on. And these are the ways it can be arranged. Okay, and these are the n number of particles that it can be arranged. So this is something which we already know. So this is the base of Maxwell distribution of deriving whatever we're going to derive now. Okay, so let's just derive Maxwell Boltzmann distribution. So first step, we are going to take a log on both sides. We are going to find out a distribution law. So what does it mean? That how ni number of particles are distributed. Okay, that is what we are going to do now. So let's just finish it off, and then I think it will be more clear to you. So what I will do is I will actually take a log on both sides. So I think all of us are clear about the laws of logarithm. So you have log of p on one side, okay, and on the other side I should adjust my screen. Okay, we have it here. So this is log of factorial n. So we can take just log of factorial n here, and then plus. So you know this if log of a into b is taken, then it is log a plus log b. So you can just take log of gi to the power ni. I can keep the summation on. Okay, the summation will be there. Mind you, the summation is not on factorial n. Then this is at the denominator, so we can just take it at the numerator, and then minus of log of factorial ni. Okay, so I hope all of us are clear about log rules. Okay, so I don't think it's very confusing here. Log of a minus b, sorry, a divided by b can be written as log of a minus log of b, and so on. Sometimes I do feel a bit inclined towards explaining everything, but I know it takes a time, and if you already know it, it's monotonous. But then I think it's important that we know, understand how exactly. So these logarithmic laws are used. Okay, we cannot do away with these things. This is there for our lifetime. And then we can again write it down this, and then you know there is a power. Log of a to the power b can be written as b log a, so I can just bring it at the front, and ni log gi minus log factorial ni. Okay, now what I'm going to do is I'm going to use an approximation. You know, factorial of something can be written in a different form altogether. Okay, and that is called Stirling approximation. I'm not deriving Stirling approximation, but we are going to use it. Okay, so the first thing is, what is Stirling approximation? So Stirling approximation says this. Stirling approximation is this: log of factorial n is n log n minus n. Okay, so if you do some statistical calculations, okay, some statistical calculation will arrive at this result. Log of factorial n can be written as log of n log n minus n. And then what we are going to do is we are going to replace it in this equation 1. So let's replace it. Log of p is n log n minus n. This doesn't have any factorial, so remains the same. And this term again becomes this. So ni log ni minus ni. And as I've told you even in the morning class, that please try to write down your notes, try to practice it, because statistical mechanics has got a lot of calculations. Okay, so if you don't write and practice, I think it will become a bit difficult. So this is something which we have. Now let's do something. So in the first session of this class, I told you about the laws of equilibrium. What are some of the conditions that we can use in the equilibrium state? We will use that now. Okay, we are going to use that now. How? Let's see. So the first term is log p on this side. So I'll take delta of log p. So I'm going to take a delta on both sides. Okay, so this will be delta n log n minus delta n. Okay, I should take it a bit down. Minus the delta of n, and then this is again log n delta ni. Okay, delta is over Ni, number of particles. The subcontainers, we are not considering any delta over that, okay? And then we have got delta Ni, okay? See this is simple. Ni into delta log of Ni. Ni into delta log of Ni, and delta log of Ni would be nothing but 1 divided by Ni into delta Ni. Just do the maths here. And this Ni is there. This Ni is this. And if you take delta of Ni, log Ni, you get 1 by Ni into delta Ni. Okay. So this and this will actually get cancelled out. You just have summation delta Ni. Okay. And then minus, it's differentiation by parts. So you can now keep log Ni outside. So log Ni is outside, delta of Ni. So that's simple. Minus summation delta Ni is equal to 0. Now you will say, why 0? Because in the first session I said that if we consider equilibrium state, okay, the maximum probability is 1 and delta of maximum probability, that means that is constant, okay. So if you basically take that, this will basically become 0. Okay, delta of constant is always 0. Maximum means it's a constant, is always 0. So this is something which you have already seen, and that's why we have a 0 on this side. So don't get confused, okay. We are just using that result, whatever we have seen. Next, we are going to use Lagrange's multiplier. Okay, but before that, I think I can show this to you. I think this is important. Okay, where is it? Yeah, sorry. Yeah. Okay, so what we have here is two terms. Okay, we have got two terms here. One is this term, which actually is there. One is this term, right? One is this term. Why? Because all the remaining term will become 0. I told you delta of Ni will be there. Okay, I think, okay, annotation. So this part will become 0. This part will become 0. Okay, this part will remain, can't become 0 because there is log gi delta Ni. Can't become 0, right? This part will become 0. Summation delta Ni is 0. This is also 0. So all these four terms will become 0 based on the argument that we have put forward for equilibrium state in the first lecture. Okay, so we have got just this term, and this term. Now, as per Lagrange's multiplier, what we do is we actually do some additional term. Okay, so this step probably you have to remember, because if I want to explain Lagrange's multiplier, you will learn it eventually. Okay, it's used in mathematical physics also. But then for now, let's assume this, that alpha and beta are called Lagrange's multiplier. Okay, and you multiply alpha with delta Ni and beta with epsilon I delta Ni. Okay, this is how Lagrangian multiplier works. Whatever is your original function, you add or subtract an additional function with it. That is what is Lagrange's multiplier is. Okay, so this is the only part that I'm not explaining right now. Okay, so this is equal to 0. So this is something which you might need to do. Okay, so what we can do is, see, all of this term has got delta Ni, this has got delta Ni, delta Ni, delta Ni. So we can just take delta Ni common and everything else will be within the bracket. So it will be log of Ni by Gi. Okay, so this is Ni minus log of Gi. So Ni by Gi, logarithmic law, and then plus alpha plus beta epsilon I. This is a minus, so it's at the denominator. Okay, delta Ni is equal to 0. So I think this is clear now, and then this is pretty much simple maths. Delta Ni, you've taken a dot with that, so you can, this is a 0 on this side, so that means if these are independent variables, this part will also be 0. So I can just simply write it down, log of Ni by Gi plus alpha plus beta epsilon I is equal to 0. So if I write that part as 0, okay, if I write that part as 0, what I have is this. Log of Ni by Gi is equal to minus alpha plus beta epsilon I, okay, or Ni by Gi is e to the power minus alpha plus beta epsilon I. I've just done a bit of maths here, and that's simple, and you see how the number of particles are distributed. Depending on the system, you will have certain specific value of alpha and beta, which are the Lagrange's multiplier, and based on that you can actually predict, or you can give a statement on how the particles are distributed, how their energies are distributed within the container or within the enclosed system. Okay, so you know in your first unit, ma'am is teaching you about the basics of thermodynamics, which you use. Okay, so there also you do understand that an enclosed system, okay, or a system which has an interaction with its surrounding behaves differently. A system which doesn't have any interaction with the surrounding and a system which has an interaction with the surrounding will behave in different ways, right? So this is the way of understanding Maxwell Boltzmann distribution. So